What's up guys, Alpha here. Welcome to my first tutorial on XGBoost. So today I'm going to introduce this library, particularly using the Python API. So the library itself was written in C++, but to be able to quickly to learn and get a feeling of how it works, using Python is a great way since it's much simpler and has a very good abstraction that kind of help us skip a lot of unnecessary details at the first step. So I think it's a great way to learn it. Just start with Python. So the library itself was developed by a team from the University of Washington, and they actually went out to found a company developing the library, and the company was later acquired by Apple. So a lot of the original member of that research team right now, they are all employee of Apple, including the professor who leading the team. So it was a really cool story about how scientists actually monetize their knowledge and make a lot of money. So okay, without further ado, let's get started. So to be able to use the library, the first step is you need to install it. So my example will be based on Mac OS. So on terminal, we will use this pip utility to install the library. Also, by the way, this tutorial, you will assume the viewer have some basic knowledge about Python and machine learning. So I'm not going to get into the theory part of this, and so I will just quickly trying to went through an example, probably in 10 or 15 minutes, to be able to get the viewers a basic view about how to run the library. So back to our install process. Then, so after you install this, and we need another library called scikit-learn. So you can using pip install sklearn to install this. So there's one tricky part is the XGBoost library. Under the cover, it calls another C++ library called OpenMP, which is a parallel computing library that this library is based on. So we need to install this part. So one easy way to install it is using the brew. This is Homebrew. It's a package management system for Linux. So you can Google this. So after you install brew, then you can using brew install libomp. Then it will install the library. So after these three steps, you probably also want to install NumPy just to go through this example, but it's not acquired. It's not also pandas, which is another popular library for doing data science or machine learning on Python. So after we install all the necessary dependencies, then importing these libraries into Python should be working. Then on my Jupyter lab here, this is the importing statements that I have. I basically just import NumPy and random. This is just built by Python, and pandas, which used to process a data frame. We'll show more examples later. And I'm also going to import this called chain text split function from the scikit-learn library. So this function is pretty neat, that would split the training data into the training set and the course validation set. So it's useful for us to train and evaluate the model. And of course, we're gonna import XGBoost itself and call it as XGB, and matplotlib. So this is the library that will be used to plot graphs like XY scatter plots on Python. So let's run this block. If there's no error message, that means all the package was installed successfully. Then the next step we gonna do is create some training data. So this is a makeup example that I created. Pretty much just try to reflect the Bay Area housing market. So to determine, like the first step, I will just randomly generate some data. In this particular case, I'm going to generate like 100,000 training examples, and then so the object I'm looking at is some house. So these are the features to describe the houses. So a house should have like a certain number of bedroom and certain number of bathroom, and the school rating, like usually there's a school district attached to a particular house, and how good this school is affects the housing price a lot. So I have a school rating, and or how close this house is to the work, like the work location. So usually, say in the San Francisco Bay Area, if you are close to, certain job locations like Google or Facebook campus, it's a very good location, considered to be a premium location, or then the price is usually much higher. So the function that I use here is just like the NumPy np.random. So this is a package provided by NumPy, and then you can call the randin. So it's gonna randomly generate some integers. The first variable 10 means like it's gonna generate a random number that's from 0 to 10, not inclusive. So basically it's 0 to 9. And the size is like how many of these numbers that I want. So the return type of this would be another NumPy array. So would be like 10 numbers, would be 100,000 numbers, and each number is like smaller than 10. So this is like my makeup example of how much the house is gonna cost. I try to make it a little bit more realistic, but this one is just for demonstration purpose. So it's just like some function that I make up here. I'm not going to too much detail about the rationale of the function, but basically it's like if the house is closer to work, it's more expensive, and if the school of the house is better, then naturally it's more expensive. And also like if you have more bedroom or bathrooms, it's more expensive. But housing market is like fluctuates a lot. There are some random factors that would make things a little bit higher or lower. So I to make that more realistic, I add a random variation on top of this. So sometimes you do see a better house sells cheaper, or a worse house sells more with a higher price. That's also possible. So this is all affected by this random variation that I put at the end. So this is pretty much what this formula is doing, but you don't need to pay too much attention to it. I just try to using heuristic to make up some random pricing model. So to demo the effect, it's like, let's say I have a 3-bedroom, 2-bathroom, and with a 9-star school rating. So this is a really good score, and 7 is too close to work here. So that means it's really close. So this house should be a really good one, because the school and the close to work, and the number of bedroom and bathroom is like in a reasonable range. Then okay, so I need to run this to define the function first, and then let's see how much it costs. It costs about $1.2 million. So it's kind of like realistic in the Bay Area market, a little bit cheaper, I would say. So Then the next step, I'm going to create a dictionary or hash map in Python. So this one has like the key is the feature names. So it's called bedroom, and then this is like the list, the NumPy array that I created previously here, and then the bathroom, the school rating, and goes to work to here to create this. Okay, so I need to run this part as well, and then I run this one, then I create a dictionary there. We can actually take a look at what this is. Oops. Okay, I went too fast. Let me go back here. So here the features is just showing it's a dictionary. It has like 4 keys, and each of the key is a NumPy array. That basically each number represents a particular house, a feature of a particular house. And then I'm going to use pandas to create a data frame out of these features. So let me run it, and then it already run because I just pressed it too fast there previously. So right now it creates a table. This is called data frame, but it's basically just a table. So this is the index of the table. That means the row number 0, row number 1, row number 2, and there are like 4 columns. So bedroom, bathroom, school rating, and goes to work. So each of the row is one particular house and with its attributes. Then I'm going to assign the price. So previously I talked about this pricing model. So on pandas, we can actually assign like one more column here to it, so that it's gonna using these 4 attributes to compute a market price for this particular house to it. So let's see how it works. So data frame would have this function called assign, and you give a name of the column that you want to generate it, and then a function, and this function gives like using the other features as input to this function, and then you would compute a value and assign that value to the 5th column here. So let me run this block, and then we can see that so compared to the previous data frame is adding one more column to here. Basically it's price. So let's see if it makes sense. So this one has like 9 bedroom and 8 bathroom, and the school rating is a little bit poor, but it's also super close to work. So overall this should be a relatively expensive house. So we see a 5.2 million price. It's a little bit pricey compared to the school rating, but all the others is a pretty big one, and also is in a pretty good location, so it's expensive. And this one has like no bedroom and 4 bathroom, so this is a really weird house. School rating is good, but it's probably like a 0 bedroom house, costs nothing. It also kind of makes sense. And this one has like 3 bedroom, 2 bathroom, relatively like a mid-sized house, and with a really good school rating, and like distance to work is acceptable range. It's not very close, but 6 is also considered to be pretty good. So it costs like $1.8 million. So it's still a reasonable assumption. So this is pretty much like how the data looks like. Now I'm going to make up some preferences. Say I'm a potential buyer in the stage of like looking for a house. Then this is my preference. There's something in my mind. Say I want to buy a 3 bedroom or probably more, 3 and above bedrooms, and 2 or more bathrooms. I want the school rating to be better than 8, and also want it to be close to work, so probably not better than 5 is like I can sacrifice my distance a little bit, but not too bad. So giving a 5 here, and also the price range that's acceptable is like 2.6. So I make up this function. So pretty much this is like just listing out the statements, like your input will be the number of those features, like number of bathrooms, school rating, and close to work, and price. And then I just list out these conditions, like the number of bathrooms should be larger than 3 and larger or equal to 3. Number of bathrooms should be larger or equal to 2, and school rating should be larger or equal to 8, and close to work should be larger or equal to 5, and price should be no more than $2.5 million. And one trick from NumPy is like, so this function is basically it's a pointer function. It's taking like 4 numbers. It's taking like 5 numbers and output 1. But what if I wanna each one of these is actually not a single number but a list, a NumPy array? Then I wanna like batch process those numbers to tell you for each row here, do I like this house or do I not like this house? Then this is the trick for NumPy provided to actually call vectorize. So I can give a function and I call NumPy vectorize, and then it will create a vectorized version of the function for me. So using this vectorized function, I can pass each variable as a NumPy array, and then the output will be another NumPy array there. So the way to do it is like in the data frame, I'm going to assign another column called like, and calling this vectorized function, and each one of the variable I'm going to pass the the vectorized version of this column to it. So basically passing these 5 columns to the vectorized function, and then for each of the row here is going to tell me do I like this or not. So okay, let me run the code, and we can see that so out of this 100,000 chaining examples, so I have 100,000 houses here, and I have like 300 of them that I like, and this 6 is just the column. So I'm basically telling this is like the filter part of the pandas. So this was my table. I'm going to look at the like is larger than 0. That means I like the houses. Then there are like 300 of them that fits this filter condition. So let's see the example here. So basically this is like all showing the positive examples and filter out all the negative examples. So you see here has like a 3-bedroom, 2-bathroom, and a school rating really good, close to work, and the price is less than 2.5. So I do like this house. Then it's assigning a label which is true here. And look at all the other examples, so it kind of looks reasonable. So for doing machine learning, this is a really common theme, basically just to look at the data and look at some individual examples to do a sanity check. Just make sure the data you're getting it's kind of makes sense to human. Like the negative example should be negative and the positive example should be positive. Alright, so we can also use like the data frame called the infer function, that basically just to give you a summary of the data. So there are like 6 columns here and the column name, and so there are how many rows of that. So there's 100,000. That's basically my training example, and the type of each example of each feature. So these are all integer, price is a float number, and lie is a boolean. And the average price of the training example is about $3.1 million. So it's pretty expensive. So kind of reflects the fact of like the San Francisco Bay Area. Okay, so now we have this like so this is our training example. So from this table it has like about 6 columns here. So the first 5 columns are the features, and the last column is the label. Then I'm going to select the first 5 columns out here to put these columns into a list. So just giving a name and this. So this is a list of string. And df, you can use the data frame to take the to use this bucket operator and giving a list out. So you would actually cut the first 5 columns out and then create another data frame out of it. So pretty much like this part is gonna cut it out, and then giving a name to it is called features chain. So this is like the feature part of our training data. And I'm going to select the last column as the label data. But here I'm going to make a little bit process because the data type, remember the last column is a boolean, but for the library to work, we need to actually make this a number. So basically I'm going to use this mask function. It's like if the df is equal to 1, then if it's equal to true, then I'll make it 1. So after you call this mask function, it still returns the same another data frame. So this is like a subset 1 column of the data frame, and you call the mask, it returns another data frame, but basically turning all the true like equals true to be 1, and then you keep calling another mask again. This time it's going to turn the value of the light equals false and turn it into 0. So the output would be the data frame at the end that like basically masking all the true value to be 1 and the false value to be 0. And so the flow is like a data frame, call mask give you another data frame, and then call mask gives you another data frame. So this is like a processed data frame. So at the end we call this like a label, the training data's label. So if we visualize it here, basically it's just like a bunch of 0 and 1s, because there are far more 0s than 1s, and there are so many columns out of here. There's 100,000 columns, so NumPy would, or data frame by default, would not display everything of this. So the 1 would be in the middle. So now, remember previously we import this function called chain text split in the beginning here. Then, okay, let me go back to here. So this is a really neat function. You can manually do this as well, but it would be good that scikit-learn provides this function for us. Pretty much you take the the feature part of your training data, the label part of your training data, and then you specify a ratio. This is called chain size. I put upon it here. So what this does is going to split the training data by 2 parts. One part used for training, and another part will be used for cross validation. And the percentage of the training data will be 80%, and the percentage used for cross validation will be like 20% of the data. So it will output like 4 variables from this function. The first part is the training data, the feature part of the training data, and the feature part of the cross validation data. So I call it test here, but I really mean cross validation. And the label part of the training data and the label part of the cross validation data. So their data types are all DF data frames here. So for the library, for the XGBoost library to work, so XGBoost library only takes one type of variable called D matrix. It doesn't take data frame directly, but it will call D matrix there. So we need to convert those data frames into D matrix. So to get a D matrix is also pretty simple. So you just call the XGB, which is the import SG library parse, and import this as an object called XGB. So we just need to call the XGB.D matrix. Okay, let me go back to the part here. So basically just need to call XGB D matrix, and then it takes two variables. So one is the feature part of the training data and the label part of the training data here. So we would take the training, the feature part of the training, the label part of the training, and give it to the D matrix and call it like the training part of the D matrix. And this is called the test part of the training data, which is used for cross validation. So similarly, we give like the feature part of the test data, the label part of the test data, and pass it to the D matrix constructor, and you would generate a D matrix of the test part of the data. Now, we are about to get to the training model part, but before that we need to give some variable, some parameters for the XGBoost library to work with. So one important factor is like the number of trees here, and the tree depth of each tree, and the learning rate, and some other parameters like the objective. So we gotta train pretty much a binary classifier. So to do a binary classifier, then the objective we use will be a binary logistic, and booster, which is the tree. So the model we're using is GBDT, so gradient boost decision tree. So to do that, you just need to have a GB tree here. And evaluation metrics is like how do we evaluate if the model is effective. So we use two metrics. One is AUC, the other is error. So I'm not going to get into the detailed definition of this metric, but pretty much for AUC it's a number between 0.5 and 1. The bigger the better. And error is like how close your prediction and the training example is. You want your error to be as small as possible. And the learning rate will be passed to this ETA. So this ETA will take the learning rate. Basically, this is like when computing the error or computing the AUC, and then you need to change some variable to minimize your training target or maximizing your training target. Then how fast do you want to go? So that's called learning rate. And the tree depths will be passed to here. So a little bit about the XGBoost tree. So pretty much like the each tree is a classifier, and then the more depths of the tree is. So in tree depths equals 6 just means like for each tree is going to use six features to determine like the score of the model. And then for XGBoost, it's kind of implementing in a series of trees. So the first tree is going to predict something in your training example and see how good it is, and the remaining it's not gonna be perfect, like if you only using one tree. And then after the first tree is trained, it's gonna do its best to predict how good this data should be, yes or no. And then you will have some residual error. So the residual error will be amended by the second tree. It's trying to amend the decision of the first tree that you make some mistake of your prediction. I'm going to correct your mistake. And then the third tree is going to correct the mistake of the second tree, and then the fourth tree is gonna correct the mistake of the third tree. So it's something like that. Usually the more tree you gonna train, and then you can make your error goes down. Like that's typically the case. And then the number of steps will be how complicated your model is, how many features are you going to use for each tree to determine like to make your decisions there. So a tree, inside a tree basically is just some if statement. If some variable is like less than this value, then I'm going to go left or go right, and then the left subtree is another if else statement. It's like if this if this feature is less than some certain number, then I'm going to do this. Otherwise, I'm going to do B, something like that. So after this model is trained, we look at the output of the model. It will probably make more sense. All right. So without further ado, after processing all the data, now it's time to actually train the model. So we need a empty dictionary. We'll show how to use this later. So the way to train the model is basically just using XGB and call the docchain method, and the return of this docchain method will be a model that will pass the parameter. So this parameter is basically telling you the parameter of the model that we are training, and the training data, which is the D matrix train, which includes the feature part and the label part, and path into a D matrix object, and the number of trees that we define here, and evaluation. Evaluation is like evals. It's like what do we want to use. So there are two parts. So we have a training part and we have a cost validation part. So the second variable is just the name of it here, but we're gonna pass like two matrices to it, two D matrices to it. The first D matrix is the training part, and the second D matrix is the cost validation part. We call it test here. So, but we name it train and cost validation. So later we will see what this name is used for here. And this parameter evals result will be stored the training process, like how does the error go down or AUC goes up, and the result will be actually stored in the dictionary. So this is the empty dictionary that we created, and we pass it here to store the how this matrix is going to change during the training process. And we do want more information to be output, so we call it like verbose eval equals true. Now let's run the program. Since the data is like really small here, the training will be pretty fast. In real applications, depends on the size of the data, it can take hours, but like for this one, it's probably take a few seconds. Like, okay, let me run the block here. Oh, so I forgot to run this part here. So run this, and then run this training. Okay, it's finished. It's probably less than 1 second. Everything is done. Now we can see that there are 4 columns output. Since we select like there are two metrics. One is like AUC, the other is error. So this is the train part is like for the training part of the data. So the name is actually specified here. If I change the name to something else, then this part will be changed there. So basically just wanna just an alias, like what do you wanna call the training part of your D matrix. Then for the training data, we can see the as the number of trees keep going up. So this is like tree number 0 and tree number 1. And then remember, like each tree is gonna amend the previous tree's error. Then we should see the AUC number goes up here, and the training error should goes down. It's like becoming smaller and smaller. And since this is the data that we are training on, so this is expected behavior, but like how generalized is the model? then we will look at the cost validation dataset, which is the part of data. Remember that we previously split the data into 80% training and 20% cost validation, and this part of data is not used by the training data, but we're gonna use the model that trained by the training data and try to predict how good the data is, how close is it to the model. Then the good thing is like we also see the AUC goes down, follow the same trend, not as fast, which is also pretty typical, but as long as it's going up there, so that's fine, and the error is also going down there. So if we see, let's say the AUC keep going up here, but here is like going up and then goes down again, then we know that we are overfitting the data, which means the model is like learning things to fit the noise pretty well, but the model is not generalized enough, so it's not going to work as good for the data that it didn't use as training. Then that's also a natural thing. But right now, I think for cost validation, everything goes up, and then the error goes down, so that's a good thing. We're not overfitting the data. Now we can actually visualize this. So remember the E results. So before that, let's actually take a look to see what's actually, after training the data, what's actually inside this dictionary. So I'm going to add another cell here. This one is just going to print out the E results. So remember, we pass a empty result to it and run it. So let's see, it's actually a dictionary. There are two keys. One is called train and another is called CV. So these are the two keys I put in here. And then there's like AUC is one metric. This is another dictionary. There are two keys. Those are these two metrics. One is AUC, one is error, and this is like showing the history of the each tree. After each tree, what the number is changing and what the error is changing, and same for cost validation here. So then we can process it. We can actually take the train part out and the AUC part, which is taking this list out, and then let's see how does it change over time. So first of all, I'm just going to this part is going to take the list out and then call a len function on it. That basically is giving me like how the number of trees here. And then this is the history. I'm going to plot the AUC change over the number of trees here. So this is like again the part of the list here, the same as this part here. And this range is just like from 0 to 10, from 0 to 9. That's the number of trees. So I have 10 trees. So this part is from 0 to 9. And this is the matplotlib function that is going to plot the x and y as its number of trees, and y is the AUC change over the tree, and assigning a label to it. And also on the same plot, I'm going to plot the cost validation AUC. And then this is just to show the legend. So let's see how it works. Alright, here you go. So we can see the blue line is the training data AUC change. It's like keep going up. Like the second tree already pretty much amend all the errors, and the remaining is like goes down a little bit and then goes up, but it's like in a reasonable range there. And cost validation kind of follows the same trend here. I would say for this particular model, probably like one tree is already the first tree is already does majority of the job there. The remaining amendment is like kind of small. And let's look at another metric. This is AUC. So the larger the better, the closer to 1 the better. And the second metric is the error. So very similarly, this part of the code is almost exactly the same, but just the key here is AUC and here's the error. And let's see how the training error is going. So basically it's like the chain, the blue light, the error drops pretty quickly, and the cost validation not drop as much but follows the same trend. So that's also a very typical state of doing that. So we can actually tune the model a little bit here. So we see that the number of trees is like varying. So what about let's like make the model a little bit complicated, see if it will do a little bit better. So to make the model a little bit complicated, the way to do it is basically you increase your number of depths here. So we're using 6 features for each tree. Then what about using 8 features for each tree, and we still keep the 10 trees here. So probably we don't need 10 trees here, because like we found that for the later trees it isn't doing too much there. Maybe we can reduce it to 7, and let's rerun the code and change the model again, and then let's update the prod here. Okay, so this one looks a little bit smooth. So you will see from the fourth tree, it's actually going to predict things pretty well there. So the cost validation kind of follows the same trend. And let's look at the error part. So this one is like, it goes down here and goes up. Like this part of going down and up is not very good. It kind of suggests it's kind of like overfitting. So in this particular case, probably we just need 3 trees will be enough. But let's try another example. How about we reduce the complexity of a tree? Previously it was 6. Let's see, like 4 and 7. How does it work? Okay, let's retrain the model and plot the curve. And the error curve. Okay. This one doesn't look very good, so I think the model is too simple. Like the training error is not going down, it's like it stays constant. Then that's not good. So let's change the tree depth to 7, and probably still number of trees keeping the 7, and retrain the model. And so we do see the training error goes down here, and AUC goes up a little bit. So I think this time looks a little bit better. Alright, so this is the error. Okay, yeah, so this error curve looks more normal. Basically your training error goes down and your cost validation error goes down, and then the AUC is a little bit tricky, but it kind of follows the same trend, and 0.994 is also pretty high range there. So that's the way how you actually tune your XGBoost model. So right now I'm satisfied with the model. I'm going to another cool thing is like we've been using like 5 features to for the prediction to see my preference. Would I like the house or not there? So I'm going to plot the feature importance here. So the function is like called sgb.plot importance, and you give the chain the model here, and the importance type is gain, and the grid equals false. So the grid equals false just means the in the plot you don't see the vertical lines here, otherwise you will see it. So let's run it. It kind of looks like this. So it feels like the model thinks the number of bedrooms is the most important feature, and then followed by the price, and that goes to work, and then number of bedrooms, and then the school rating. So I mean, it kind of makes sense. It's like not exactly what the human, like me as a human in mind. Probably I would think the school rating and the price is the most important factor, but this feature importance is basically for the model is like, how does this feature in the tree is giving you most information gain, and how important is this feature is used as a deciding factor to give a score. So if you want to know more about that, you can probably read the paper, but like intuitively, it's just like the more this feature is get used, and the more important it is. So we can also actually, so one more thing is like the plot we are showing here is like this number is actually going out of bound. We can actually using so matplotlib here is actually return the axis here. We can actually adjust the size of the image. So now I just adjust it to like 25 as x-axis and y-axis as 7. Let's see how it works there. Okay, so that looks much better. So everything is inside the plot here. So if we don't, we can also change the grid here, make it to true, and then you can see the actually the grid showing here. Okay, so if I'm happy with the plot, I can also look at the number of the feature importance. So here you just need to call model.get f-score. You're actually showing the importance of each feature. So here the most important thing is the price, 19, and bedroom is 17. Yeah, it's a little bit weird. See, like I feel this two pro is not consistent with each other. Here is showing the most important feature is like 19 is the price, and the bathroom is like 13. I wonder if this model is correct. Yeah, I think it's correct. So okay, anyway, like this part is a little bit weird, but this is the feature importance of the model here. I guess probably something related to this this importance type here is probably showing a different importance type. And then at the end, we can actually evaluate. Usually, we can re-evaluate the number. Oops. We can re-evaluate the number using the test images there, and then see how it does for the evaluation set. So at the end, you got like a 0.99, and then really small error. So it does good for the evaluation set here. So the last step usually we do is to use the model, the train model, to predict something for new data that we never seen before. So I just make up two examples here. One is like I have the first house. It's like 4 bedroom, 3 bedroom, and school 9 goes to work A costs like $1.5 million. So this satisfies the mental model I have for a good house there. And the second house is a really small one, 2B, 1B, and school is kind of bad, and it's kind of far away from work, and price is cheap, which is good, but like it's not satisfy the standard. Then we can okay, so you can use this makeup data to predict how good the model works. So I'll construct my feature map again. Basically, this is giving the two examples for 4 bedroom. The first one is 4 bedroom, and the second one is 2 bedroom, and bathroom 3 and 1, and school rating and 9 and 4, and cost to work is like 8 and 3, and the price is 1.5 million to 400,000 here. And then from the this map, I'm going to create a data frame, and from the data frame, we're gonna create a D matrix. So notice that we only pass one parameter here to the D matrix. That means this part, there's only the feature part, is no label part here. Usually it takes like two parameters. The second one is the label part, and there's no the label part here because we are predicting it. We don't need the label part. and then we predict. We use the model to predict how good this is. So let's see how it works. Okay, so I think I probably should put let's not run this part so far, and then this predict outputs another like a NumPy matrix here. So here you go. This is like pretty much outputting the probability of like the probability of how good these two models are. So the first one is like telling me like the 47% chance that I would like this house, the first house. Cannot double click. Okay, so there are 47% chance that I would like the first one, and there's only 24% chance I will like the second one. So it kind of makes sense, the data. It kind of makes sense. There's a higher probability that I would like, there are twice as many probability that I would like the first one rather than the second one. So this, you can choose your threshold to tell you it's like or not, but this is basically just giving a probability based on the model. And now we can actually do an evaluation on here. So I think we can actually print out a statement here. So this is like my prediction, and plus this one. Let's see. Okay, I cannot do that. I need to turn this into a string. Oops. So this is the string, and this is for print. Okay, there's one more parenthesis here. This is for print, this is for predict, and this is for str. Alright, here you go. So this is my predicted probability of the two houses. And then I'm going to run an evaluation. The same thing for doing AUC and error. So pretty much I need to give a label to this chain example. I'll assign a 1 to the first example and 0 to the second example. And then now I create a data frame for the label, and then we pass this two data frame into the D matrix. The first part is the feature part, the second part is the label part, and create this D matrix. And then the generated D matrix I call it to eval D matrix. I'm going to pass this to the model for it to do an evaluation. So now the next step, I'm going to call the model.eval method and pass a D matrix. This D matrix contains the feature part and the label part here. Let's see how it works. So it outputs like AUC equals 1 and training error like 0.5. So I think it's doing an okay job there. The training error is a little bit high. And now we can actually save the trained model. The way to do it is called save model here. So this model file is saved. So this is a binary file, it's not human readable. There's a way to get a human readable. Is actually, instead of calling save model, we can call dumb model, and it will output a text file. So let's do it, and let's see. So this is actually the tree model it actually trained. So booster 0 is like the first tree number 0, and booster number 1 is tree number 1, tree number 2. So we should have like how many trees? 7 trees out of it. So from 0 to 6, there are 7 trees. And then inside the tree is basically just some if statement. Pretty much this is node 0, the node of the tree, and the first split is on the school rating. So if school rating is less than A, If true, I'm going to know 1, and if it's false, I'm going to know 2, and if it's missing value, I'm going to 1 here. So for node 2, so if my school rating is less than 8, then that's true. It's gonna output a negative number here, so it's probably like it will give a low probability in this case. And then otherwise, if it's no, so that means like my school rating is larger than A, larger or equal to A, I'm going to the node 2 here. So node 2, the first node is gonna split on bathroom. So if my bathroom is less than 4, and if yes, I'm going to node 3. If it's no, then I'm going to node 4 here. So that's pretty much the logic of the decision tree, how the decision tree is working. So each time it goes to leaf, that's the value that you predict for the first tree. And then it goes to the second tree, and then it has all the leaves values here. So you go through each decision tree, 7 of them, and then you sum the value of the leaf, each leaf node, and the output will be the probability that you are getting here. So this how these numbers are formed. Okay, so that's just a very brief introduction about like XGBoost Python API, and basically it just like give you a feeling of like how a machine learning engineer work using this library, and how does a model, like although this is a makeup model, but I'll try to just use this example to demonstrate how this library works and what kind of things that we can do. Alright, if you like this video, don't forget to give me a like, and don't forget to subscribe or turn on notification if you don't want to miss content like this. Thanks for watching. Bye.